Hello class, I'm going to walk through the solutions for week 12. Invent a task, write a word problem that would elicit a partitive conceptualization for the division operation below. Okay, so let's do that first. So when you're given just these two numbers, if this is partitive division, then the divisor here will be a multiplier. The dividend is a product, and so we are looking for the missing multiplicand. Missing multiplicand goes with partitive division. And so it's probably easier to start with this right here. We're missing the multiplicand, and the multiplicand is the component of our multiplicative structure that has a rate unit here, which is a something per something. And you can really put anything you want here. There's so much freedom. It could be a unit of weight per unit of time per unit of money, unit of number of brownies per classroom. Like there's really so many different things you can say here, but you do want to pick units for which fractional amounts make sense. And since 28/3 is one of our numbers, I don't want this unit to be children, for example, because we don't want partial kids. So I'm going with quantity or units that fractional amounts make sense, like pounds and containers. Okay, so once you decide whatever units you want here, the denominator unit, the containers, should match the unit of your multiplier, and the numerator unit will match the unit of the product. So that is a guide for knowing what number should wind up going where. And so sometimes it's easier to start off with this type of thing and say, okay, well, I have 4 containers and 28/3 pounds, and I'm looking for how many pounds per container. So this is a fair sharing partitive model here. And so I said 28/3 pounds of water is equally split and poured into 4 containers. How much water is in each container? So there's my word problem. Now I'm going to model this to get an answer. I began by drawing the 28/3 of pounds of water. So each of these from here to here is 1 pound. And 28/3 pounds is the same thing as, let's see, 3 divides into 28 9 times. So you could express 28/3 as, let me write it this way. 28/3 is the same thing as 9 1/3 pounds. And let me put the unit on there. 9 1/3 pounds, or 28/3 pounds. So you can clearly see we have our 9 pounds in my drawing here. 1, 2, 3, 4, 5, 6, 7, 8, 9 pounds. And then there's an extra third over there off on the right. So you have 9 1/3 pounds. Well, if I break each pound into thirds itself, you can see that we have the 28/3. Because each of these is a third of a pound. And if you were to count those out, right, you would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28/3 pounds. And we want to share this between 4 groups. Now there's lots of ways you could have done this. Because 4 divides into 28 evenly, we could do vertical partitioning again and start separating groups. And I'll do color coding. If we do 28 pieces divided into 4 groups, so 7 pieces per group. So each container will get 7 of these thirds. So the first container will get these 7, just different colors. The next container will get 7 more, so there's 5, 6, 7 right there. There's another 7 thirds. The third container, let's go to a new color, will get another 7 thirds, which should take us to right there. And the final container, the 4th container, gets the remaining 7 thirds. So that was one way to do this. And you can see that we have let's use the blue one here to illustrate. We have 7 thirds pounds per container. You could have also have done cross partitioning this way. Break up the total amount of water, the total weight, into 4 groups by doing 4 horizontal lines. I'm not going to actually do that cross partitioning because 4 divided into 7, so I could stick with the vertical partitioning I'd already done. Just had to figure out how to break 28 pieces into 4 groups, and that was easy. 7 pieces per group, and each piece was 1/3 of a pound. And then, of course, our division, we just do the rule that if you have a fraction divided by a non-fraction, that you can just multiply the 3 and 4 and put that in your denominator. So 28/12, which simplifies to 7/3 pounds per container. Number 2, invent a task, write a word problem that would elicit a quotative. All right, so quotative corresponds to a missing multiplier. So sometimes it's easier to start with this structure here and identify where the question mark should be. We're looking for the multiplier, so that's where the question mark goes. We know we're given the 3 and the 7/5. Right, the divisor here is going to be the known multiplicand, and the 7/5, which is the dividend, will be the product. And again, you can pick any units you want right here. But once you pick those units, the dollars per pound is what I picked, then this denominator unit will correspond to the unit of the multiplier, and this numerator unit, the dollars, right, will correspond to the unit of the product. And so then I just invented a situation. So we clearly know how much something costs per pound. We know how much money we have. We just don't know how many pounds correspond to that. So this question could be nuts are sold at $3 per pound. How many pounds can you buy with 7/5 dollars? And this would correspond to a quotative division task. Now, there are lots of ways to model this. I'm going to model it with drawing the $3 that corresponds to a pound and the 7/5 dollars that I actually have. So in this first drawing, we have $3, which corresponds to 1 pound. So that means each of these blocks right here is $1. Now we actually only have 7/5 dollars. So I drew a second block to represent how much money I have, if that's how I want to think about this. So we have $1 and an extra 2/5. Right, we have 7/5 total, 7/5 dollars. And the question is, how much money or how many pounds can this amount of money buy? Well, this is really a simple matter of overlapping this with our pound structure and reunitizing so that this is a new whole, because that's a pound. And just how much is shaded? Well, we can clearly see that if I were to continue the partitioning, let me bring that back down. If I were to take the whole pound and continue the partitioning, so break these into fifths, I'll do this a little bit sloppily, break that one into fifths, and break this last one into fifths, this last dollar into fifths, then you can see that the amount of shading, which goes up to here, we've shaded, well, how many total little pieces do we have in the entire pound? Well, there's 15 pieces there, and I've shaded 7 of them. Right, so looking at the purple, we've shaded 7/15 of a pound. And so the answer is we can buy 7/15 of a pound if I have only 7/5 of a dollar, 7/5 dollars. And then, of course, even with the quotative conceptualization, we can still do the algorithm where if you have a fraction divided by a non-fraction, that you just multiply the denominator with the divisor. So the denominator of the dividend, which is 5, with the divisor, which is 3, multiply those, you get 15. That makes your new divisor, or sorry, your new denominator here. Multiply the denominator with the divisor. I know a lot of D words I'm saying here. This is called dividend, this is the divisor, and this is the denominator. The 5 is the denominator of the dividend. And anyway, we get 7/15 pounds. Number 3, express the task below as a missing multiplier, missing multiplicand, or missing product multiplication statement with units. Indicate whether multiplication, partitive division, or quotative division will resolve the task. Resolve the task and draw a picture to depict your reasoning. So 5 cups of syrup have a total mass of 2/3 of a kilogram. Determine the mass of 1 cup. So as soon as you see determine the mass of 1 cup, then we know that we're looking for the unit rate. We're looking for the multiplicand. We want to know how much there is per cup, how many kilograms there are per cup. So that tells me the question mark should be with the multiplicand. The multiplier should be measured in cups, so that's where the 5 goes, and the product should be in kilograms, and that's where the 2/3 kilogram goes. So we're trying to say if we have 5 cups, and we're going to multiply by so much kilograms per cup, and we want the total to be 2/3 of a kilogram. So we just got to figure out essentially how to break 2/3 into 5 pieces. And each of those pieces would be how many kilograms are in a cup. So this is the missing multiplicand task, which means that the kind of division we're going to do is partitive division. Actually do the division down here. This is partitive division. 2/3 kilograms divided by 5 cups will give me, and then I use the algorithm to get the answer. All right, we just multiply the 3 and the 5 again to get this 15 right there. So 2/15 kilograms per cup should be the answer. Well, let's see if we can get a picture to justify that. And I began by drawing, there's lots of ways you could do this. Some people begin by drawing the 5 cups. They'll say, okay, let's go ahead and draw 5 cups and then figure out how to split 2/3 kilograms into these cups. I'm actually going to do this by drawing the 2/3 kilograms first. Okay, there's multiple ways you can do this. I'm just demonstrating one. And I want to, so here's my picture. That whole block is 1 kilogram, and I've shaded in 2/3 of a kilogram. So let's label some things. Right, that is, the entire block is 1 kilogram. So we've shaded 2/3 of a kilogram, and I want to effectively break 2/3 of a kilogram into 5 equal parts. So I'm going to use cross partitioning to do this. So I'm going to try to break this into 5 equal parts. Oops, let's do black, yep. And I'm only worried about the green right now. Just trying to break the green into 5 equal parts. And if this doesn't look perfect, that's okay. We can use our imagination a little bit. And so we break that into 5 parts, and we want to just keep one of those parts. So I'm going to shade in red here one of those parts. So 1 cup, which is what's shaded in red, is how much of a kilogram. So that corresponds to how many kilograms. Well, if you were to continue the extension of these lines across here, you would see, okay, well, 1 kilogram is all of this. And there are 15 slivers, if you will, right? So if I were to, color coding is extremely helpful when you're doing something like this, because I can color code just one of these pieces and say, okay, well, how much is just that piece? And just that piece only is 1/15 of a kilogram. But it also corresponds to 1/2 of a cup. But let's not worry about that. 1/15 of a kilogram is that blue piece. And the 1 cup gets 2 of those pieces equivalently. So these 2 red pieces. And so we're going to have effectively 2/15 kilograms contained right in this 1 cup right here. Because we started with the green, and the green was split into 5 pieces, and we focus on the size of one of those pieces in terms of kilograms. So here's an image that helps support that. When you take 2/3 of a kilogram and split it into 5 groups using cross partitioning, then one of the groups will correspond to 2/15 kilograms. Number 4, this one, similar instructions. Jordan can bicycle 8 1/2 miles per hour. Determine how far she can go in 3/4 of an hour. So you have to really be mindful of the units to know where the multiplier is, or the multiplicand. That's really the one to focus on. When you see 8 1/2 miles per hour, well, 8 1/2 is the same thing as 17 halves. That's the multiplicand. So that is given. Which means that the multiplier should have units of hours so that it matches that denominator, and the product should have the same unit as miles to match that numerator. And the other good bit of information is how much time. It's 3/4 of an hour. So the 3/4 goes here. So I know the multiplier and I know the multiplicand. I don't know the product. That's what I'm going for. So this is a missing product task, which means we're going to use multiplication to solve it. We don't need to use division. We just got to figure out how to do 3/4 of 17 halves. And I began by drawing 17 halves. 17 halves miles per hour. So let's be clear about what is going on here. We have each of these blocks, when I say block I mean from here to here, stands for 1 mile. And you can clearly see we have a total of 8.5 of those, right? We have 1, 2, 3, 4, 5, 6, 7, 8, and then an extra half shaded. So 8.5 or 17.5 miles. And the entire thing, shaded that is our 17.5 miles, and we know that that corresponds to 1 hour. That's how far this person, Jordan, can bicycle in 1 hour. We're trying to figure out how far Jordan can go in 3/4 of an hour. So I want to do 3/4 of this. 3/4 of what's shaded, green. I want to focus. I'm going to use cross partitioning because I can't really do 1/4 of 17. Well, I would have to get partial pieces, and I don't want that. If this had been like a 16/3 miles and I broke that into 4 pieces, that'd be easy because then I'll get 4/3 per piece. So I'm going to use cross partitioning here, whereas if you backtrack to here, we were able to avoid cross partitioning because 4 divided nicely into 28. But here we're trying to break 17 pieces into 4 equal groups. Well, that's 4 doesn't divide into 17. So to find 1/4 of 17 halves, cross partitioning is useful. So let's go ahead and do that. I'm going to cross partition this. Let's do just a different color here. Let's first cut in half. And I'll try to make this one look a little bit more precise. There we go. I'm going to copy, paste this. Now cut each half in half. That looks decent enough. Okay, and let's do some shading in red. So here's 1/4 of an hour shaded. Because remember that the entire green that I had shaded initially corresponded to 1 hour. So there's 1/4. Now I want to do 3/4 though, so I also get to shade in 2 more quarters. Oops, this is not what I intended. Let's make that look decent. Okay, so I'm going to take the time here to shade in 3/4 of the green. Okay, so now the red is shaded 3/4 of the green. And we want to figure out exactly how many miles that corresponds to. Well, if you were to focus on each little piece, yeah, let's do these little pieces right here. That piece right there is how much of a mile? Well, keep in mind that all of this was 1 mile. So that top left piece is 1/8 of a mile. The question is, how much time does that correspond to? Well, if you're to look at the entire hour, right, the entire hour is this entire green block. Break that up. Well, how many of those little tiny pieces we have here that correspond to that entire hour? Well, we have 17 across the top and 4 down across the bottom. We have 17 columns and 4 rows. And 17 columns and 4 rows, multiply 17 and 4, and we get 68. So the little blue box is 1/68 of an hour. Did I do that right? Let's make sure. All right, so we have this entire, I'm just double checking. We have this entire box right here is 1 hour. And that has been broken up into how many pieces? We have 17 across and 4 down, and 17 times 4 is 4 times 20 minus 60, 68. That's 1/68. Just making sure I'm doing that right. But the question now, though, is how much is shaded in red? So we have 17 by 3. We have 51 out of the 68 shaded in red right now? Oh, of course. I'm thinking in terms of hour. That's not what we're after. That's why I'm confused. 51/68 is the same thing as 3/4, and that's just 3/4 of an hour, which that's how we got this. We started with an hour and did 3/4. We want to figure out how many miles is shaded in red. So this part here didn't even really matter. Each little blue box is 1/8 of a mile. So the red, you do all the red, corresponds to 70. How many do we have here? We have 3 rows that are red and 17 columns. So 17 times 3 is 51. Here we go. We have 51 total little boxes, and each one is 1/8 of a mile. So 51/8 miles is how much is shaded in red. There we go. And that is our answer that we get by doing the algorithm. 3/4 of 17.5 will wind up being 51/8. Okay, number 5. Similar instructions. Express the task below. Okay, let's just read the task. 3 ounces of quinoa provide a daily serving of protein. Determine how many servings correspond to 7 3/8 ounces. Okay, so the multiplicand is given. It's subtle, but we have 3 ounces of quinoa go with 1 serving. So that is our multiplicand, 3 ounces per serving, which means our multiplier should be in servings and our product should be in terms of ounces. Determine how many servings correspond to 7 3/8 ounces. Well, 7 3/8 is the same thing as 59/8, so that's the product. That's in ounces. It's the servings we're looking for. So we're trying to find a multiplier. This is a missing multiplier task. This means that we're going to be doing quotative division. I already did the division down here. We do the product divided by the multiplicand, and that will give us a multiplier. And now a picture, though, to justify this answer. Okay, I've drawn 2 pictures. I've drawn that we have 7 3/8 ounces right here. So each of these boxes that you see is 1 ounce. And you can clearly see we have 7, 1, 2, 3, 4, 5, 6, 7, and then I did 3/8 of this next one. So we have 7 3/8, which is 59/8. And then up here, I did 3 ounces together to make 1 serving. And the question is how many servings correspond to 7 3/8 ounces. In other words, how many reds make the green? This should look like a familiar task that we did in exercises. We're doing a multiplicative comparison here. We're trying to figure out how to scale the red to make the green. So we're looking for a scale factor, if you will. How do I scale red to make green? And when you're looking for a scale factor, you're looking for a multiplier. Right? We're trying to say, hey, what do I multiply 3 by? How do I scale 3 so that it's equal to 7 3/8? And so this, if you're thinking scale factors, you would still have the same multiplicative structure. And we're going to do this by just, I'm going to copy this a couple times. Let me do some unshading here, and then do some more shading and say, okay, well, how much, if you're to break this all up into each of these 3 blank boxes into 8ths, right, what would that look like? We have to be half, 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 and half. So just a bunch of halves, and let me just copy and paste that. And we are shading up to this amount. So we try to figure out how much of a final serving that we have right there. Well, serving has a total, if there's 8 per box here, and we have 3 boxes, then we have a total of 24 little vertical segments here in a serving, and we have 11 of them shaded. So we can see that from here to here is 11/24ths of a serving. All right, keep in mind that we started with 7 3/8 ounces. We're trying to figure out how many servings that makes. So it makes 2 full servings and then 11/24 of a final serving. And let me move this down just slightly. And our visual justifies an answer of 2 and 11/24. Or you can make that 24/24 plus 24/24 plus 11/24. That's going to be 59/24. The same answer we get by just using the algorithm with a quotative meaning for a division. This is 2 and 11/24 servings. There are lots of other ways you could have thought about this. You could have started with 1 serving and then say, hey, what do I have to do to a serving to get down to just one of these little slivers here? Right, so just 1 sliver would be 1/24 of a serving. And then just ask yourself, okay, well, how many of those slivers do I have to do to get this? And that's a total of 59 slivers. And so if you take 1 serving and you boil it down to this unit size right here, this little sliver, that's 1/24 of a serving, and then you'd have to do 59 of those to reconstitute what's in the green. And so you can also see this scale 1 serving down and then scale it back up to reconstitute the green. And when you see it that way, I see, instead of thinking of mixed numbers and 1 serving plus another serving plus a part of a serving, I can see this as multiply 1 serving by 1/24. All right, that'll take 1 serving down to 1/24 of a serving, and then take that little sliver there and scale it up by 59 times. So in other words, if I do 59/24 of a serving, I'll reconstitute the green bar. So it's another way of thinking about this 59/20, how you get the 59/24, but maybe a little bit more, a little more directly. Oops, I did not want to erase that. Oops, I'm making all sorts of mistakes here. Let me just copy that. Struggling. Please work. Copy. Paste. Thank you. Let me erase that. Okay. Anyway, our answer is 2 and 11/24 servings, or 59/24 servings. Number 6, resolve the 2 tasks below and draw a picture for each to depict your reasoning. So Nathan built a rectangular picture frame with an opening that is 4/3 of a meter by 7/10 of a meter. So what I've done for this one here, since 4/3 and 7/10 are not too far from 1, I began by drawing this black square that you see right here. That black square is 1 meter by 1 meter. So that represents an area of 1 square meter. We want to figure out what fraction of that square we wind up actually shading. Like how many square meters we actually wind up shading. So I partitioned the top edge into tenths, and I focused on 7/10 of a meter. I partitioned the left edge of my black square into thirds, and then I did 4/3. So that went beyond by an extra third. So now I started with the square, and then I figured out the rectangle that is, oops, didn't want to do that. A rectangle that you see right here that vertically is 4/3 of a meter and horizontally is 7/10 of a meter. And the question is, how much area is in the red as compared to the, in terms of square meters, as compared to the amount of area that's in the black, in units of the amount of area that's in the black square. Well, there are lots of ways to do this. We could continue our partitioning of these, extend them all the way down. Now, this isn't perfectly done, but it's good enough. There should be 7 columns, effectively. They should all be equal. You can clearly see that they're not, but that's all right. And then we have these rows. Okay, now let's focus on exactly how large is just that portion in blue. If you were to take that portion and repeat it, how many times would it repeat in order to refill the original square meter? All right, you can clearly see, I hope you can clearly see that you would need let me do this in a way that I can. So there's that portion right there. So we have 1, 2, it's not quite the right length, but you get the idea. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across, but then you have 3 rows. So we have 30 of these that would fill up this entire square meter. So one of them, that one right there, in blue, is 1/30th of a square meter. And then now the question is, well, how many of those make up the red? Well, you would have 7 across the top, but then 4 across, or down vertically, right? So we're 4 by 7 would make up the red. So in other words, 4 by 7 is 28. So we have 28 of these little blue boxes that make up the red. So the area of the red, box should be 28 copies of 1/30th. So in other words, 28/30ths of a square meter. We can get that from this image without ever using the algorithm. Now, of course, to find the area, you do length times width, and the algorithm for multiplication fraction says multiply the numerators and then multiply the denominators, and that gives us that 28/30ths as well. The same answer we get when we actually think this through and understand what's happening. And of course, that boils down to 15 or 14/15ths of a square meter. In other words, if you were to take these extra pieces down here and try to work them back up into this empty space here in the square meter, you would see that we would only get so far. We'd only be able to fill up so much of it, and in the end we'd be able to deduce that we have 14/15ths of the square meter filled in. I'm not going to take the time to do that. I'll leave it to you to think about that. Here's a scaling task. Sarah is 1 1/3 times as tall as her daughter, Dominica, who is 1 2/5 meters tall. Determine Sarah's height. Well, I'm just going to translate this into a sentence. Sarah is, so Sarah's height. I should say Sarah's height, or you can say she is times as tall as. But Sarah's height is 4/3 times, 1 1/3 is 4/3, 4/3 times as tall as her daughter Dominica. So we want to scale Dominica's height by 4/3 to get Sarah's height. Well, Dominica's height is 7/5 of a meter. So we do a scale factor, right? We think of this as a unitless scale factor. We're going to multiply that unitless scale factor by 7/5 meters, and we're going to get an answer in terms of meters, and that's going to be Sarah's height. So we just got to figure out how to scale 7/5 meters. So I drew several pictures here to show this, and there's lots of ways to do this. Here's maybe a new one that we haven't looked at before. 7/5 meters. Okay, so in this diagram, let's be very clear about what we're seeing here. Each of these little boxes here is 1/5 of a meter. Right, we can see we have 7 of them. 1, 2, 3, 4, 5, 6, 7. So 5 of them make a whole meter. So we have 1 2/5 meters essentially, or 7/5 meters. Right, that's how tall Dominica was. 1 2/5 meters, or 7/5 meters. And I want to scale that by 4/3. Well, I'm going to think of scaling by 4/3 as a 2-step process, which I didn't really write here. Let me move this over here. To do 4/3 of something, think of it as doing first 1/3 of it and then doing 4 of those. Right, this is an excellent way to think of a fractional multiplier. And ultimately that will yield the 28/5 meters that you would get if you simply did the algorithm of multiply the tops and then multiply the bottoms. You're going to get the same answer. But this is conceptually the good 2-step process. So to find 1/3 of 7/5, well, 3 doesn't divide into 7, so I'm going to use, and I could use cross partitioning here, but I'm going to actually use vertical partitioning within partitions. To find 1/3 of 7, right, we have 7 things here, seven boxes right here. Each box is 1/5 of a meter. I want to find 1/3 of that. I'm just going to break each box into 1/3 and then shade it. So that's exactly what I did here. So I did 1/3 of each of the 7 boxes. And so what's shaded in green, let's write that over here, is currently 1/3 of 7/5 of a meter. That's what's shaded. But then I'm going to take these shaded pieces and stack them end to end. There's 7 shaded little pieces, and if you put them end to end, you get this much. So down here you can see 1/3 of 7. We really have 7/15 of a meter. Keep in mind that 1 whole meter was to there. That's why I did this little extra vertical bar right there, so just to help me remember where 1 meter is. Otherwise, it's very easy to get lost in this forest of vertical lines. So 1 meter is right here, and what's total shaded here is, well, how many pieces are there? There's 15 pieces, and 7 of them are shaded. So we have 7/15 of a meter currently shaded. And now what I want to do is iterate that 4 times. I want to do the 4 times. So I'm going to indicate, so there's 1 7/15. And we have to do another 7, so 2 plus 3 plus 2. So there's another 7/15. And then 2 plus 3 plus 2. There's another 7/15. And then 3 plus 3 plus 1. And there's our final 7/15. Maybe different colors for each 7/15 would be nice, so you can see that there are now 4 of them. And once I found 1/3 of 7/5, and then I did 4 copies of that, now you can see how many meters we're working with here, or that we have total. I'm going to put the extra partition right there so we have all equal size pieces. And as far as meters are concerned, right, we have 1 whole meter right here. And then we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 out of 15 of the next meter. Right, so in mixed number, our answer would be 1 and 13/15 meters is how tall, Domenica's mom, Sarah, is. This could have been done, like I said, this could have been done with cross partitioning instead, or there's even other ways you might have been able to think about how to do this. Seven. So the rectangle below represents 1 candy bar, shaded in a representation of 3/4 of that candy bar. We call this a serving. Okay, so in this picture here, some people changed the size of the bar and they went with different size bars, but I wanted everyone to be consistent, so I drew this rectangle for you and said that's 1 candy bar. We have to work with that and be consistent from drawing to drawing. So let's be clear again. We have from here to here is 1 bar. And from here to here is 1 serving. It's 3 pieces out of the 4. So the next set of instructions, repeat your drawing above but without the shading. So I didn't repeat the red shading. I put the green shading in after, but I kept the bars in there, the red vertical lines. Use cross partitioning to shade in a representation of half of a serving. Well, I didn't want you to, since the serving is composed of 3 pieces right here, right? This serving has 3 different pieces. Cutting 3 in half, you could do that and say 1 1/2, but I wanted to avoid breaking, going like this. This is another vertical partition. I wanted to do cross partitioning, which means now do a horizontal. So take this row, right, this row of 3 boxes, and cut it in half horizontally. So, and then shade that. So there's what's in green is half of a serving. You'll notice it's not half of a bar. In fact, it's 3/8 of a bar, but it's half of a serving. This is worth mentioning. Let's go ahead and correspond. We have 1 serving corresponds to 3/4 of a bar. 1/2 of a serving corresponds to 3/8 of a bar. All right, what's shaded in green here is 3/8 of the entire bar. And now we want to do 5 half servings. So now I want to do 5 copies of it. And what I did is I took one row and I simply made 5 copies of that and just did it vertically like this. So there's 5 copies of a half of a serving. And now we want to figure out how many bars this is. Well, if you take a half of a serving and you multiply it by 5, then you should take 3/5 of a bar, multiply it by 5, and you should get 15/8 bars. But let's see how this picture supports that answer. Let's go to a different color. We want to focus on how much green we have now. Well, let's start with how much blue there is right there. That blue represents 2 things. It's either 1/3 of a serving, sorry, 1/6 of a serving, right? Because 6 of those blue things make up this serving right here. So it's 1/6 of a serving, but that little piece there corresponds to 1/8 of a bar, right? Because 8 of them will make the entire bar. Remember, the bar is the original rectangle, and a serving is this truncated rectangle. It's 3/4 of it. So the blue box is 1/6 of a serving, which is 1/8 of a bar. But then we want to say, well, how many bars is all of this green? Well, we have 3 columns and 5 rows, so we have 15 of these little blue boxes, and each blue box is 1/8 of a bar. So you can see why we're saying that we have 15/8 of a bar here. So how many candy bars are shaded in the image directly above? The answer is 15/8 bars, or 1 7/8. Now, one thing you could do also is you could take these extra pieces and start filling in the gaps. Like you could take those 2 right there and put them in this empty spot, and then try to reconstitute bars this way, and you're going to see that you're going to get 1 7/8 bars, which is the same thing as 15/8 bars. Some people did that, but I'll leave that visual off. So the work above, we had 3/4 bars of a bar per serving, so that's the multiplicand. We know we wanted to ultimately be shaded in 5/2 servings. And when you multiply the number of servings by the number of bars per serving, will give you the number of bars. And so the multiplicative structure here is, 5/2 servings times 3/4 bars per serving equals 15/8 bars. And that is confirmed by the algorithm, right? 5 times 3 is 15, and 2 times 4 is 8. So we just confirm this 15/8. So this exercise is meant to think how to find 5/2 of a serving if you knew that how many bars was one serving. And we did 5/2 by doing a half and then doing 5 times. So that 2-step process, partitioning followed by iterating. One serving cut in half, and then that half serving iterated 5 times. And number 8, the rectangle below. Now the rectangle below was originally just this right here. Right? So that rectangle right there was 1 candy bar. Shade in a representation of 5/2 candy bars. So I first cut that candy bar in half, and then I did 5 of those. So 1, 2, right, 3, 4, 5. In other words, 2.5 candy bars are here. And there's 5/2 candy bars. We will call this shading a serving. So this is now one thing. It's one big serving. The servings here are much larger than in the previous problem. You got to eat a lot more candy to constitute one serving. Repeat your drawing above, but without the shading. So I just repeated all the red stuff, but I didn't shade in the red. Use cross-partitioning and shade in a representation of 1/4 of a serving. So cross-partitioning, again, I went horizontally, and I did 1/4 of a serving. Remember, a serving was up to this point. And I wanted to do 1/4 of that, and I did it horizontally, and that's what I shaded in green. So there's 1/4 of a serving. If we were to do some sort of correspondence, let's do this. Let's say that 1 serving corresponds to 5/2 bars. And what we just did now is 1/4 of a serving. How many bars is 1/4? How much is shaded in green here? Right, so let's focus on one of those pieces right there. I see a total of 1, 2, 3, 4, 5 of those green pieces. And how many of them make an entire bar? Well, 8 of them do. So there's 5 green pieces shaded, and 8 of them would make an entire bar. So in other words, we have 5/8. 1/4 of a serving corresponds to 5/8 of a bar. right? And to go from 1 serving to a quarter serving, you divide by 4, or multiply by a fourth, scale by a fourth. So multiply 5/2 by a fourth, it gives you that 5/8. And now we want to do 3 of those. So we want to now scale up to 3/4 of a serving. We'll scale this up by 3 times the amount, and that takes us to 15/8. I've shaded in 3 rows now. And again, each of these, I'm going to emphasize in a blue box. Each of these little slivers right here, that is, you can think of that as 1/5 of a serving. Right? Because, oh, sorry, that's not 1/5 of a serving. That is oops, the serving is, I was thinking it's 1/5 of a row, but the serving is all of that. And that would be 5 times 4 is 20. There's 20 blue boxes in an entire serving. So what I've shaded here is 1/20th of a serving. And that corresponds to 1/8 of a bar. And what's shaded in green is 15 of those blue boxes. So you have 15/8 of a bar shaded in green now. So that's how many candy bars are shaded in the image directly above. And when I say directly above, I meant to focus only on this image here. I think some people focus on all these images and like combine them together to make something, but that's not what was intended. And then to put this into a multiplicative structure, we have 3/4 servings times 5/2 bars per serving. It's the bars per serving is the multiplicand. That's the 5/2 bars per serving. It gives me a total of 15/8 bars. We confirm it using the algorithm. We get 15/8 that way. And then notice when you compare this with the last task, which also gave us 15/8, but the role of the multiplier and multiplicand switched, right? In task 7, we had, in this task, task 8, we had 3/4 servings and 5/2 bars per serving. And in the previous task, task 7, we had 5/2 servings and 3/4 of a bar per serving. So conceptually, the two situations are very different. The serving sizes are not at all the same. The thing we're calling a serving is very different. But however, they both yield the same answer, 15/8 bars. So we're seeing here that even when you're working with non-whole factors, right, 3/4 and 5/2 are both not whole, that multiplication is still numerically commutative. Although I would argue it's not conceptually commutative, because the two scenarios are wildly different. I mean, they're just not at all similar conceptually. The serving sizes are not consistent. However, they both wind up yielding the same numerical amount, 15/8 bars.